Alright, this is Physics 1C for October 1st. Tonight we're going to be talking about resistors. Alexander? Uh-oh. Alright, there we go. Alright, tonight we're going to be talking about resistors, combinations of resistors and how they work inside of circuits. Just as a general reminder of like what a resistor is. In the diagrams that we see tonight, the resistor is basically going to look something like this. There's going to be this little zigzag kind of line, and an R to represent or to stand for resistance. What they are effectively devices that when electrical current passes through them, so if you have current, which we usually label with I, if there's current that flows through the resistor will have the effect of heating up. It effectively kind of tends to slow down the current, one way you can think about it, I suppose. And it has properties often that will allow it to warm up. Inside of a lot of devices, you've got resistors. We've talked before about how things like toasters and electric stoves are examples of resistors that you might see in your home. Generally, some kind of device that takes electricity, turns it into heat. Alright, so resistors in series, the idea here is that if I give you a circuit, and let's say that we have a circuit where I have a voltage source here, delta V, and I connect it up to two resistors, and we call this one resistance 1. We call this one resistance 2, or resistor 2. And we connect them into a complete circuit like this. Then this is generally labeled as the positive side of our battery here. And we're going to have electrical current that's going to flow through our system from the positive around to the negative like this. And it'll flow through both of the resistors. When we connect a setup like this, where we have a battery and two resistors, one thing I can say is that any current that flows into this resistor here, because it's a flow of charges, is going to have to flow out this resistor, and that same current is going to show up over here as well. So you're going to get the same current through each resistor. That's one of the things that we can say about resistors in series, which is that when you have resistors in series, they're going to have the same current. It's going to pass through all of them. Each resistor, you get the same current when they're in series. This is pretty much coming from the idea of like that charge has to be conserved. If I had more current flowing in here than I did coming out of here, that would imply that some of the charges just disappeared into the environment or something like that. And generally the way that these circuits are constructed, none of the charges are escaping. So, yeah. The other thing that we can say is, and this is something we did with capacitors as well, that if I want to look at the potential difference, delta V, between 2 points right here, that's going to be equal to, if I call this delta V1 and delta V2 to represent if I were to place a multimeter around these, a voltmeter, if I wanted to measure just the voltage across this resistor, or I wanted to measure the voltage just across this resistor here, then the total voltage would end up being equal to delta V1 plus delta V2. And then what we do is we're going to plug into this equation our equation that we have from Ohm's law that says that the potential difference drop across a resistor is going to be equal to the current flowing through that resistor times the resistance R. And our goal here really is to take this picture and simplify it down into just one resistor, where we call the resistor we say it has an equivalent resistance REQ, and we're still going to have the same delta V here, the same current I is going to be flowing through here. In this scenario, we'll do the right side first. So for each of these resistors, delta V1, you're going to have I times R1 is what delta V1 is going to be from our Ohm's law equation. And then for delta V2, it's going to be I, sorry, that's a little sloppy. It's going to be I times R2. And on the left-hand side, we think about what's going to happen when we condense it down. There's going to be the same current multiplied by REQ. And this gives us a really simple result. All the I's cancel out, and we get that the equivalent resistance when you connect things in series, you're going to get R1 plus R2 plus however many resistors that you actually decide to combine together. Okay? Does that all make sense? Anyone have any questions? I should say something about current and current measurements, for which we can pull up the PhET website, and we can kind of construct circuit diagrams. Let me do that real quick so we can let's find the one we want. This one in particular is really useful to learn things about circuits because it allows us to kind of build whatever we want. Give it a moment to load up here. So a series circuit, we would get by, see, here's all the pieces that you have. You've got wires, you've got resistors, you've got batteries, you've got capacitors, you've got different types of voltage sources. A battery is considered to be a DC or direct current voltage. You've also got light bulbs here. So if I wanted to construct a circuit like the one we just made, I could just take wires here. These wires are considered to be having no resistance, I believe. So we would connect up our resistors here. We can set the value, so that's 10 ohms. We could change it to, let's say, 50 ohms. Notice that it actually changes the way it looks on here, too. Get another resistor, put a wire in between them. Another wire here. A lot of these extra wires are completely superfluous, but just to kind of make it look similar to what we saw in the picture there. So there we go. You can see there's current flowing. And just to make the current stop flowing, what we'll do is we'll throw a switch in here so we can turn the current on and off when we want to. Just likes to split junction. There we go. Okay. So we'll use this switch. And so now, what is the, let's see, show value. Let's have them have different resistances if they're not exactly the same. Let's make this 25. Or let's use 100. And then we can show value on this one. Change the voltage if we want to. Let's make the voltage some multiple of these, so let's do like 15 volts. And maybe you guys can make some predictions right here. The next thing we want to have is a voltmeter. So in our picture here, if I place my voltmeter around my battery, and the battery has, show value, 15 volts, then it's going to read 15 volts. That's the voltage that you get between these 2 points. Because the conductors themselves have no resistance, you're going to get the same voltage difference across here. Well, you won't. It's 0, right? Because of the switch. But if we close it, there we go. So I guess one thing you could do here is you could try to predict something. What should the current flowing in the circuit be? What would the current flowing in the circuit be? Can anyone tell me? I don't know why it keeps removing those. So let's look at what we just did here. 150 divided by 15. So let's look at the equation and see if that makes sense. So first of all, what's our equivalent resistance for this circuit going to be? 50 ohms and 100 ohms. What's the equivalent resistance? 150, right? You switched it. That's right, Meower. So what would the current be then we predict then? You take the voltage, you divide by the resistance. So 0.1 amps. Okay, let's see if that's true. Now, the thing about measuring voltage, you need 2 points to measure voltage. You also need 2 points to measure current. But one thing with current is we actually have to put our ammeter into the circuit. That's how real ammeters work. But there you go. You can see that it reads 0.1 amps. Okay, we'll leave this on here. So another question I could ask you, knowing that the current is now 0.1 amps, what would the current, what would the potential difference on the 50 ohm resistor be? If I want to put this, so I want to put, one thing here and one thing there, what's it going to read? How do you figure it out? You type the equation you would use too, probably. 50 ohms times 0.1 amps. Yep, that's right. So 50 times 0.1 is 5, right? Yep. That reads 5 volts. Okay. What would the other one read? The total's 15. This one's 5. What's left over? You've got 10. These two have to add up to the voltage of this one. And that's all there is to it. It's pretty simple. Resistors are reasonably straightforward. Okay. I guess another thing we could do is we could ask what would happen if I changed this resistance to 50 ohms. I don't know. What if I changed it to, like, let's say 100 ohms? What's going to happen to the current? Is it going to go up or down if I increase the resistance? Should go down, right? Because you've got more resistance. And it does, to 0.07. 0.07 is going to be coming from, again, 15 divided by the total, which is 200. So 15 over 200, about 0.07, probably 0.075 or something like that, right? Or I have to wait. That'll be 15 divided by 200. What is that? Not as simple to do in your head or whatever, but it'd be 0.075, right? Yeah, 0.075. So this thing isn't exactly super accurate. It's only going out to a third digit, and it's not rounding, but okay. So, all right. There we go. Resistors in series, pretty simple. So let's do resistors in parallel now. Pretty similar calculation. For resistors in parallel, we kind of create like a stack. So you have, here's your battery, plus minus. We give it a potential difference we call delta V. And now we stack two resistors on top of each other, giving each one of them a separate path to the battery. So the way you know you have, oops, not R2, there we go. So R1 and R2. The way you know you have parallel is if I can draw a complete path that goes, you know, through the resistor and back to the battery, and I can do the same thing for the other one that goes through the resistor and then back to the battery. So two separate paths. That means that each one of the resistors has its own connection to our battery down here. And again, this is how your home is wired. Anytime you plug something into the wall, every single appliance that you plug in gets the same voltage from the wall because each one of them is plugged in parallel into your home circuit. Okay, in this type of a scenario, what we learned from discussing things with capacitors was what's the potential difference across each of these as compared to this? Is it split in half? Is it the same? What's the potential difference across R1? They're the same, right? So that means that all of these are going to have the same potential difference, delta V on this one, delta V on this one as well. And that's between the 2 points across the resistor. When you measure potential difference, you do so with the voltmeter and you do it across the resistor. So if they have the same potential difference, you get the idea that if they have different resistances, they're going to have different current, right? And that's true. As the current flows out here, if I was to call this current I, as it goes into this junction, this allows some of the charges to go up and some of the charges to go to the right. So if we call the current flowing in the middle segment I1 and the current flowing in the outer segment I2, then we can make a statement that is due to a law we're going to learn in a second, which is whatever current flows in here, if it splits into I2 and I1, then that current should be related to those two. In particular, we should be able to say that the current that flows into that node or that junction should be equal to the sum of the currents that flow out of it. Hopefully that seems like a reasonable thing to say. I mean, if current flows in, it has to flow out, because charge is conserved, it doesn't just come from nowhere. And then what we do is we say, okay, well, our goal, as before, would be to take our picture right here and reduce it down to, you know, just an equivalent resistor, to one resistor that had the same battery hooked up to it. So here's delta V, there's REQ, the equivalent resistance of those two, and again, the same current I flows here as fluid into these two. So then what we do is we just, once again, we apply Ohm's law, and we say the current I should be equal to delta V divided by the equivalent resistance. I1 should be equal to delta V over R1 delta V1, sorry. Just delta V over R1. Then I2 should be delta V divided by R2. And then, of course, we cancel out the delta V's, and this tells us that the equivalent resistance, 1 over Req, is equal to the sum of the inverses of the individual resistors that we have connected in parallel. And if we connect more resistors in parallel, we would add those in. Other way to write this would just be that Req is equal to like R1 to the negative 1 plus R2 to the negative 1 plus how many ever you have, and then you need to take this whole thing and put it to the negative 1 power. So that's our definition of equivalent resistance. Sum up the inverses and flip it. Any questions? If you think back to capacitors, when we added capacitors in parallel, you just added the capacitances up, right? So it's kind of flipped. If you remember that. When you added capacitors in series, you did something like this, but when you add capacitors in parallel, you do something like this, right? So capacitors are exactly the opposite in terms of these two. They just flip. Okay? You don't have any questions? If not, we can do a problem. We could also come back here and kind of just verify that what we just said is true. If we decide to construct something like this here, we'll remove this one. So there's one branch, and what we'll do is we'll put ammeters in each branch so we can actually measure the current in each one and verify that it's in fact different. Get a wire here, get a wire there, open the circuit for now. A resistor here, a resistor here. Let's change the resistance to, like, let's say 75. And then change the resistance here to maybe 50. Or let's do 25. Okay. You notice these colors change. Each of the colors actually indicates, and this is how commercial, like resistors, like you went and bought them at a store or you bought them online, you'd see these little colors on them. So that the red actually represents a 2, the green represents a 5. Since this is 75, that's why the second one's green, and then purple is for 7. The black line right here represents times 10 to the first power. So it's 75, or times 10 to the 0 power or something like that. All right. Oh, I put 3 in here. Didn't mean to do that. Here, we'll just remove this one. We'll just remove this whole thing. All right. So we'll go... Whoa, what did that connect to? That was weird. Go add some wires. One right here. One right here. So these are connected in parallel. If we show the values here and here, can you guys tell me what would the equivalent resistance of this one be? Let's see if we can use this to predict what the currents are going to be. What would the equivalent resistance of these two be? 75 ohms and 25 ohms. There's our equation, right? So we'd be doing, see if you can do the calculation yourself. Yeah, 18.75, okay. Once again, in this case, the equivalent resistance here ends up always being smaller than the individual resistances. Whatever the smallest one is, this is going to be smaller than it. So in this case, 25 ohms, your equivalent resistance has to be smaller than that value. All right, so then what should our currents be? What would I be equal to? For I, we got to do delta V divided by Req. Delta V in this case was 15 volts, divided by 18.75 ohms. You get something in amps, 0.8, okay. And then I1, the current flowing in the bottom branch. Let's see, what was our schematic here? This was 75 ohms. So it would be delta V, which is 15 volts, and then we divide by 75 for this one. And then for I2, you're going to be doing 15 volts again, and dividing by 25 ohms. Let's see, this one I can probably do in my head because it's like 3 over 5, so it's 0.6 amps. Okay, and then this has to be 0.2, right? Because it has to be this minus this. Let's see, 3 over 15, which would be 1 over 5, yeah, 0.2 amps. Okay. All right, let's see if that bears out. If we turn this on, we expect the... And there's some things you can see about this too, which is that when the current splits, like this, the current through the smaller resistor is going to be higher. So let's kind of visualize that on this thing. So if we connect our circuit, we get exactly that. We get 0.8 amps right here. We get 0.6 amps up here. You get 0.2 amps down here. The current's flowing in here. Technically, the current's flowing to the left, right? But it's showing us electron flow here, I believe. And you can visibly see the rate at which these balls are moving here, that the ones through the 75 ohm are going slower. So the current tends to flow faster through the smaller resistor. That should be obvious, but I think like visualizing it is important. And yeah, there we go. You have any questions? Any questions at all? Okay. So going back to what we were discussing. So we now know how to combine resistors in parallel, resistors in series. So let's do a problem where we do both. Did I already go by it? Where is it? I put it right here. That's strange. 1 second. Oh, it's over here. Okay. Okay. Very straightforward problem here. We've got a network that's drawn for us here. As you can see, these little red squiggly lines are your resistors. You've got a 3, a 6, and a 4 ohm resistor connected, as shown here. We want to find the equivalent resistance of the network, and we also want to find the current through each resistor. And the source of EMF has negligible internal resistance, so that's what the R equals 0 thing here. Remember last time we talked about how the batteries themselves can have resistance, and a lot of the problems will do. We're just going to assume these are like ideal sources, and we're not going to worry about that. So, we did problems like this before with our with capacitors, right? And what we had to do is we just kind of crunch down the picture until it turns into just one resistor. And you go through and you just determine, like, okay, we look at these two resistors here. Are they connected in parallel or series? They're parallel, right? So if they're in parallel, what do they turn into? So we still have our 4 ohm resistor here. What do those two crunch down into? One over 3 plus 1 over 6 is a third plus a sixth. So 1 over 3 plus 1 over 6. So that's like 2 sixths plus a sixth. You get a half. You have to raise it to the negative 1 power. You're going to get 2 ohms. So this is 2 ohms. 18 volts still. Reduce it down one more time. 4 and 2 are in series, right? So what's the total resistance? 4 plus 2, so 6, yeah. Pretty easy. Now we go backwards. We say, okay, 18 volts and 6 ohms, that's going to give us a current. It's a different color. It's going to give us a current that's going to be equal to 3 amps, because we're always using this equation, delta V equal to I times R. So if I have 18 volts and I divide by 6 ohms, I'm going to get 3 amps. Okay. But then we look at this picture here and we say, oh, well, these are a series, right? So what do I know about the current here compared to the current through these two? Equal. Yep. So we're also going to have 3 amps of current flowing through here, which means for this resistor here, I could take 4 times 3, right? I times R. I, R. So current times resistance gives us 12 volts right here. 18 volts minus 12 volts gives us 6, but we can also find it the other way. 3 amps flowing through a 2 ohm resistor. 3 times 2 is 6 volts. Isn't this so much easier than doing these problems with like the electric field calculations you guys have on your these circuit problems? They're a lot more straightforward. Okay, going from look at the 2 ohm resistor now. It had a voltage between these 2 points, which on this picture was basically point C and point B. Right, C and B right there. So if the potential difference between C and B is 6 volts in this picture, it's also 6 volts in this picture, right? So you're going to have 6 volts across both of these, right? We also already know for this one right here that you're going to have 3 amps going in here. So for these two then, if they have 6 volts of potential difference between these two, then we could figure out the current. For this one, it would be 6 over 6, right? 1 amp. And then for this one, it's going to be 6 over 3. So that one's going to have 2 amps flowing through it. Splitting up like that and like that. And you can see that 3 amps splits into 1 and 2. Okay? That's it. You don't have any questions? Okay. So, some problems you can do this. Not all problems will be able to do this, though. The only time you can really do this is if what you have is like a single battery and a bunch of resistors. Okay, sometimes you'll be able to do it within a given problem, as we'll see, but for the most part, unless it looks kind of like this, you're going to need to do something a little bit different. And what we're going to do that's a little bit different from those type of analysis, we're going to use something called Kirchoff's laws. I probably should have gone and looked up how to pronounce this, because I hear it pronounced Kirchoff, I hear it pronounced Kirchoff, I hear it pronounced Kirchoff. I don't know. I don't know how to pronounce it. Regardless, Kirchoff's laws apply to slightly more complicated circuits. Let me give you an example of a circuit that would not work with the previous... well, here's one right here. We're going to do this problem. You have 2 batteries. Okay, the existence of this one battery right here prevents you from using Kirchoff's laws now. And here are a couple little more complicated ones that we're going to be using to describe how Kirchoff's laws work. So, these networks cannot be reduced by simple series parallel combinations of resistors, okay? You've got a battery here. You've got a resistor here. You've got a battery here, you've got a resistor here, and you've got another resistor. Actually, in this case, I guess these resistors are representing the internal resistance of the battery. Over here is another one. I believe this one cannot be reduced with Kirchoff's laws. These can't be reduced with series parallel reduction, because these are not really in series or parallel in this case. It's a little more complicated. If it wasn't for this resistor in the middle, you would be able to. Anyway, so these are examples of circuits that you can't really use what we just discussed. But what we can do, didn't mean to click that, what we can do is we can use Kirchoff's laws. Is that a Wheatstone bridge? I think it is, yeah. I believe that's a Wheatstone bridge, which is something that we'd be using as one of our labs in this class. But yeah. All right, so the next thing we do is, okay, yeah, so Kirchoff's laws, what are they? There's 2 of them. There's something called the Junction Rule. The Junction Rule states that if I have a junction wherein I have a wire, and that wire splits up into other pieces, like let's say like this, this, and maybe like this, that if I have some current that's flowing into that node, let's say I have some current that I call I1 that flows in here, then that current is going to split into 3 in this case, where this is going to be called I2, I3, and I4. And what the junction rule states is that if I add up all of the currents that are flowing into my junction, they should add up to 0, as long as you define incoming current to be positive and outgoing current to be negative. Okay, so we define that's not how you spell that word. We define current as positive coming into the junction, and then do I need to write the opposite? Define current as negative going out of the junction. Okay, so in this case, what the junction rule would tell us would be that I1, which is positive, minus I2 minus I3 minus I4 should be equal to 0. That's what the junction rule would say. A junction is usually a place where you have like a T, or a place you have to have at least 3. If you just have 2 things connected together, that's just going to be a corner. So this is not a junction here, but this point and this point are both junctions. Okay? That's the junction rule. Another way this ends up getting written, then, if you just rearrange it, would be that I1 should be equal to I2 plus I3 plus I4. And if you want to think about it like that, you can. This is often easier to remember. It's like whatever current flows in has to be equal to whatever current flows out. Okay. The other Kirchoff rule is called the loop rule. Okay. The loop rule states that if I sum up the voltage drops around a closed loop, that the sum of the voltage drops should be equal to 0 around a closed loop. Okay, a loop is something like this. You draw a loop like this, and you have rules for what these delta V's are. Okay, the rules for what the delta V's actually represent. If you have a resistor, it's going to be something like I times R. If you have a battery, it's just going to be the EMF of the battery, okay? But it's going to depend on which way the battery is pointing. The rules that we use for these look like this. These are the rules. So a loop involves going around in a loop like this. And these are sign conventions that we use, and you kind of just got to memorize them. So if I have a battery and it's oriented like this, and I go in the same direction from negative to positive, I get a positive E right here. If I have a battery that is pointed this way, it's going to be a negative E, okay? The travel is in this direction. If you go from negative to positive, it's like a potential increase, right? You can understand this because which point on the battery is at a higher potential? Is it the negative side or the positive side? Which point is at a higher potential? Which point? The negative side or the positive side? Positive side, right? This could be like 10 volts. This could be 0 volts, okay? So if I jump from here to here, I've gone uphill, right? I've gone from a low potential to a high potential. That's why my delta V, right? You're summing up delta V's. That's why it ends up being positive. Does that make sense? It's like you've gone from the bottom of a cliff to the top of a cliff. Now you've got a bunch of energy. If I flip that battery around, well, there's 2 ways to think about this. So if you're going opposite to the direction of the battery, right, then you're going from high to low. So the change in V would have to be a negative number, right? So do these make sense? Before we move on to the current, do these 2 make sense? We could draw the convention that's written here. It could be drawn in a slightly different way. We could leave the battery pointing like this, and we could have it so that our travel direction was this way. And by travel, it means loop. You're going to be using this to generate equations, basically. All right. This one would also give us negative E. All right, so let's look at the conductors. If my direction of travel is against the current, I'm going to get positive IR. This is going to be the higher potential. Why is it the higher potential? Because positive charges are going to tend to flow in the same direction as the current. The way that I think about this is you're kind of gaining energy, right? When you travel upstream, you have the ability to easily flow back downstream, so you're gaining energy by going upstream. This would be like, imagine you're on a river and it's flowing in a certain direction, right? If you swim upstream, then the stream will naturally carry you back downstream, right? So by swimming upstream, you're gaining energy. By traveling against the current, you're gaining IR. I times R, because that's the potential. If your direction of travel is downstream, or if your direction of travel is in the same direction as the current direction, then you're going to get negative IR. Okay, do these make sense? You guys are scared of sign conventions. That is, I don't know what to say about that. You can kind of memorize these if you can think about like the physics behind them. You think about energy. So when you go from a lower potential to a higher potential, you're going to get a positive. And that's basically the rule. Does anyone have any questions? Okay, these rules will make a lot more sense when you actually see them used. They're really simple, honestly. So we are going to use, I think this is the first circuit. We're going to do both of these, but we're going to use this circuit. This came from a homework problem from another textbook. So what are we going to do with this? Let's see, I'll keep the sign conventions here so we can kind of see it while we're doing it. There was a question I just realized I should answer it. Why is there the summation notation if the negative signs show up? I don't understand why that's a problem. The summation doesn't always mean that you're summing positive things. You can still sum negative things. I mean, think about alternating series, right? One, you know, like you can have a positive, negative if you want to. Yeah, if we sum up all the currents, they have to be equal to 0, but current going out of the node is negative. Does that make sense to you? How you can get 0 then? Okay. It's just like when you do sum of all forces in physics 1A. Sum of all forces equal to 0, kind of similar thing. You can have positive and negative forces that balance each other out. Similar kind of balancing thing. Yeah. Okay. It's not a great notation. It's better to just remember the idea. I think in both cases here. So okay, let's look at this problem here. I think that's, yeah, we can see everything we need there. So our goal with this problem is to we're going to use the rules, okay? And what we want to do here is we want to find the current flowing through each branch, okay? That's one of the things we want to do. We want to find the current flowing through each branch. There's going to be a total of 3. And that's it, actually. We could also ask things like, what's the power dissipated by these resistors? Maybe we do that at the end. But for now, we really just want to find the current in each branch. Now, to do this, we need to, the first thing you do when you do these problems, and you'll have a few of them on your homework, the very first thing you want to do is you want to label currents if they're not given to you in the problem, okay? It makes absolutely no difference what direction that you choose for the current, okay? So what I'm going to do is, let's use blue for current. I'm going to say that the current flowing through this upper branch right here I'm going to say it points this way, and I'm going to call it I1. And I'm going to repeat this because I'm going to get this question a lot. This is really important. It makes absolutely no difference what direction I choose. I could choose either direction. It does not matter. You just pick one, you know? You just pick it. Don't be afraid. It will work. Doesn't matter. I'm going to choose the current flowing through this path right here to go this way. Although I don't have to. Ultimately, I don't really know what direction these currents are going to flow, but looking at the battery, I think this is probably right. Doesn't matter. And then current flowing in the outer branch right here, again, I don't know where it's going, so I'm just going to randomly assign that it goes to the right. Okay. So we're going to solve all these. I don't know that the directions I've chosen here are correct. If one of them is pointing opposite to the direction of the real current, my answer will just come out as negative, and that's fine. So this is step one. You will do this on all these problems. Before you do any calculations, before you ever use an equation, you draw these on here. It's like doing a free body diagram in physics. You know, you got to pick directions for your forces, right? So here we pick directions for currents. We'll just throw them on the diagram. The next thing that we can do is we can apply the junction rule. So the junction rule, you don't need to write this down every time, but just to remind you which one we're doing, tells us to look at junctions. And I'm going to say that the only places where you have junctions here are here and here. We're only going to use one of them. We're going to use C. At point C, I have I3 flowing in, right? I3 continues up this. It's the same I all around here. This is all I3. I3 right here. This is I3 all around the outside here, okay? So I3 flows in, I2 flows in, and then I1 is the one that's in the upper bracket here. So I1 flows this way. So my loop rule, I said that we're going to make anything flowing in positive, right? So I2 plus I3 minus I1, because I1's flowing out, is equal to 0. That's my first equation. I have 3 unknowns, so y'all tell me, how many equations do I need now? How many more equations do I need, or how many total equations do I need? 3. Yeah, exactly. 3 unknowns, you need 3 equations. So the other unknowns will come from the loop rule then. If I were to rewrite the junction rule for this point right here, and I encourage you to do so right now, you'll find that you get exactly the same equation. So by using the junction rule twice, we're not going to learn anything. We got to use the loop rule. There are 3 total loops that I can choose from here. I do not need all of them. A junction is any point where there's like a T. You need to have at least 3 lines that cross each other to have a junction. If I have just 2 lines like a corner, the corner doesn't mean anything, right? Because these are wires. Remember, these are wires, okay? So the wires are never, in a real circuit, they're not going to look like this. It's just going to be wires. They bend, okay? But this point is a junction because you have at least 3 lines that are connecting there. You need 3 or 4 or 5 lines connecting together. Does that answer your question? Ash, does that answer your question? Okay. All right, so next we want to do the loop rule. Let's move this over here. So that's our junction rule equation, right? Let's do the loop rule now. We'll just say that right there. Make sure we have a lot of room for this. Now, there are 3 loops that we can find in this problem, and I'll label all of them here. It makes absolutely no difference what direction you choose, but you have to choose a direction. You're either going to go clockwise or counterclockwise. Clockwise, counterclockwise. This is going to get a little bit messy. So what I'm going to do is I'm just going to draw it like that. I'm going to call that loop 1. And then I'm going to go like this, and I'm going to call that loop 2. All right, and say loop 1. We're summing potential difference drops. We're going to start from, let's start from this point right here. We're going to go from B to C to F to E. We're going to go, you don't have to write this now. We're going from B to C to F to E. That's the loop that we're traversing, okay? All right, I'm going to tell you what this one is and how I know what it is, and I'm going to ask you to try to write down the equation for yourself for the second one, all right? So starting from this point right here, I'm going in a loop here. That means the direction that I'm traveling is from the negative to the positive. What do I want to write down? I'm either going to write down negative 10 or positive 10. I'm going from negative to positive. Which one do I write down? Negative 10 or positive 10? Am I gaining potential or am I losing potential when I go from the negative side to the positive side? Am I going uphill or am I going downhill? It's the first one. It's positive E. You're gaining potential, exactly. So the first thing I'm going to write down for loop 1 is E. And then when I come to here, I've got a resistor. I've got to write something down for resistor. I've got this rule over here, right? The rule says that if you're going in the same direction as the current, if I travel in the current direction, so current is to the left and the travel's to the left, or if the current is to the right, like it is here, and the travel is to the right, same direction, I'm going to write minus I2 times 6 ohms. And I just realized right here, I don't need to write E. I can actually write 10 volts here. So 10 volts. So 10 volts minus I2 times 6. That's what I get out of these first two here. 10 volts going from here to here, minus 6 times I2. Keep going. We get to here. Y'all tell me what I'm going to write down now. The loop continues this way, so we're traveling, the path is to the left. Do I write down positive or negative 14 volts? It's going to be 14. Is it positive or negative? You're gaining, so it's positive, exactly. Okay, we keep going. Okay, now the current I2 is flowing in the same direction as my path again. So you tell me, what do I write down? Or sorry, I1. The current I1 is flowing in the same direction as the loop path. So I'm going to write down I1. It's going to be multiplied by 4 ohms. Do I put positive or negative right here? Am I going downstream or upstream? It's negative because you're going downstream, basically. I always think about this in terms of a river. You're at a lower potential here. You're farther downhill. Okay. And what's this all equal to? Well, according to the loop rule, the sum of all the voltage drops has to be equal to 0. That's loop 1. So that's an equation we can use right there. So the question is, does that mean that all the resistors will have the same sign and the batteries will all have the same sign? That is a question that I can't parse. Maybe somebody else can answer the question for you. Maybe they understand what you're asking. Yeah, be careful about simplifying. We don't want to simplify it. Yeah, it depends on the current flow. Remember something, Ash, that I did at the beginning. Or not Ash, sorry, Mr. Miars. Remember something that I said at the beginning. I picked this, right? And Jose's right, it does depend on the current flow. I picked I2 to the right. That was a choice. It was a choice, right? Had I chosen I2 to flow to the left, this would have become a positive. So yeah, it depends on the current flow. That's the right way to answer that question, I think. All right, let's do loop 2. In fact, I want y'all to take a minute or two to do loop 2. Can you write down the equation? And in order to have an equation that kind of looks similar, let's go A to D to C to B. So we're going to go from point A to point C to point... Nope, that's not right. A to D, I left one out. We go from A to D, and then to C, and then to B. And then back to A. I want each of you to write down what you think it is. Just write it in your notes, and then you can verify when we actually do it. If you want to put it into the chat, you can, but wait a minute or so. People can actually write it down. So take a minute. I'll give you 1 or 2 minutes, maybe. Write down what you think this should be. And don't share it in the chat until after the 2 minutes is over. Okay, that should have been about 2 minutes. Does anyone want to say in the chat what the equation they got for this one is? Okay, negative 2i2. Oh, sorry, negative 2i3 plus 14 volts minus I1 times 4. Oh, see, loop 2 is just the bottom, actually. Maybe you did... It looks like you did another loop, which is fine. We're going to talk about that next. That's okay. Somebody else want to try? I think the way you wrote that is correct, though, Nathan. That's going to be what we call loop 3, so keep that in mind. We'll come back to that one. But what you wrote is correct. Okay, so Adil says... Tyler's first. Okay, Tyler said negative 2i3. That's correct. If we're going in the same direction as the current down here, so you do negative 2 ohms. Oh, let's use black. So you do negative 2 ohms multiplied by the current flowing in that section, I3. We're coming up into this segment right here. You both said that you get 6 times I2. Tyler's saying 6 times I2, that's right. And it's positive because we're going against the current now. So it's going to be 6 ohms multiplied by I2. Your loop is to the left, your current's to the right, so they're opposite to each other. That's where the positive sign comes from. And then for the battery right here, you're going to get negative 10 volts. Negative because we're going from positive to negative now. All of this should add to 0. Okay? I think all the answers are right. Ash, I think you need to have... The second term should be I2 and not I3, probably. Alright, good job. Okay, now that we've done this, we can solve our problem. Because our only unknowns are our currents, we have 3 equations. One thing I'll say before we move forward is that we could have chosen to do another loop where we went all the way around the outside. That would have been an effective loop to choose as well. You could call that one loop 3 if you want to. And if we had chosen that one, then what we would get is what, who was it? Nathan said, right? You'd get negative 2i3. And then we come all the way up to here. You get plus 14 volts. And then you get minus 4i1. It gets kind of annoying to keep writing the ohms over and over again, so we're going to drop those for the rest of the things we do here. Okay. So before we move on, we've got these equations. There's equation 1 right there. We'll call this one equation 2, and we'll call this one equation 3. Does anyone notice anything about loop 1, loop 2, and the equation for loop 3? I guess what I'm asking is, could we use these 3 equations? Yeah, we'll talk about matrices here in a second, Ash. That's not what I'm looking for here. What do you notice about those 3 equations? Loop 1 plus loop 2 equals loop 3. I think that's right. I'm pretty sure that's correct. If I was to take equation 2 plus equation 3, I'm going to get this one right here. If you notice the 10 volts plus the negative 10 volts, those cancel. Positive 14 volts, the only thing that's left over. What about the I2 that shows up here? Well, it's negative 6i2 here, and it's positive 6i2 right here. So if you add these 2 equations, those would also cancel out. So all that you'd be left with is negative 2i3, that comes here, and negative 4i1, that comes right here. So what does that mean? What does that mean? If I have 2 equations, loop 1 and loop 2 equations, right? And I have a third equation that happens to be equal to the sum of the other 2, can I use these 3 equations to solve for my currents? As in, can I avoid using the junction rule? Can I just use this, this, and this together? Do y'all know the answer to that question? You think so? Ash says no with a question mark. You have all three variables there, yeah. So you meet the condition of three equations and three unknowns. If you have three equations and three unknowns, are you guaranteed that that you can solve? You're not, right? What has to be true? So you may have learned this in linear algebra or algebra 2. A minimum of 3. Okay, that's really specific, Ash, but why does that happen? Oh, it's already 7 o'clock. Probably should. Okay, Maurer says, when one equation is simply the summation of the two other equations, then you really only have two equations with three unknowns. That is exactly right, Mr. Meowers. This isn't a new equation. It doesn't tell us any new information. It doesn't tell us any new information at all. I think the phrase you might use in your linear algebra class is that you need to have three equations that are linearly independent of one another. You can't have two of them that actually represent the same line. Right? So it won't, yeah, so just keep that in mind when you're solving these problems. You're allowed to write as many loop equations as you want, but you can't only use loop equations. You're always at least going to have to use one junction rule when you're solving these problems, okay? And the junction rule is the easiest one to get right anyway, so but it is something that people will do, okay? So don't only use loop rules. We're not going to use this equation. It's not like it's wrong. We could use loop 3 and 2, or we could use 1 and 3, or we can use 1 and 2. It's, yeah. All right, we need to take a break. We'll come back and solve these here in about 10 minutes or so. So it's 7:12. We'll continue. You're welcome to solve them over the break if you want to, but we'll go through the full solution afterwards. And as Ash has mentioned, one of the ways in which we can do this is by using matrices. We'll do that as well.